Gravity, in its most fundamental form, is a force that binds the universe. It governs the motion of planets, stars, galaxies, and even light itself. In Newtonian physics, gravity was portrayed as an invisible force acting at a distance, instantaneous. This led to early debates and questions that would linger for centuries. But in the 20th century, Einstein's general theory of relativity revolutionized our understanding of gravity. Space-time, the fabric of the universe, was no longer just a passive stage but an active player. Mass bends this fabric, creating what we experience as gravity. Gravity is a manifestation of curved space-time and the way it propagates through the universe. Its speed is central to understanding the fundamental structure of the cosmos. Einstein's general theory of relativity proposed that gravity was the result of mass bending space-time, and this bending propagated as ripples, gravitational waves. When massive objects like black holes or neutron stars collide, they create disturbances in space-time that travel outward at the speed of light. These gravitational waves carry vital information about their sources, and the ability to detect them has opened up a new window for astrophysics. For decades, the idea of gravitational waves existed only in theory, and no instruments were sensitive enough to detect such subtle distortions. Then, in 2015, the LIGO Laser Interferometer Gravitational Wave Observatory detected the first direct gravitational wave signal from a black hole merger. It confirmed a key prediction of Einstein's theory: gravity moves at the speed of light. The concept that gravity travels at exactly the speed of light has major consequences for both the fundamental laws of physics and our understanding of the universe. But it wasn't always accepted. Why it matters: the speed of gravity and Einstein's vision. In Einstein's general theory of relativity, the speed of gravity must be finite to preserve causality, the fundamental principle that cause precedes effect. If gravity were instantaneous, events could influence each other faster than information could travel, causing paradoxes and violations of the laws of physics. The speed of gravity, then, guarantees the integrity of time itself, ensuring that the universe's sequence of events remains intact. The speed of light is the upper limit for information transmission in the universe. This limit applies to everything from photons, light, to gravitational waves. Thus, Einstein's equations predicted that gravity would propagate at this same speed. The fact that gravity moves at light speed means that the behavior of massive objects is constrained by the same speed limit that governs all other phenomena. LIGO and the sensitivity to gravitational waves. LIGO's 2015 detection of gravitational waves was a historic achievement. The interferometers at LIGO are so finely tuned that they can detect distortions in space-time as tiny as 1,000th of the width of a proton. This level of sensitivity is mind-boggling when you consider that gravitational waves have to travel billions of light years to reach Earth. The LIGO detectors use lasers to measure tiny shifts in distance between mirrors placed kilometers apart. When a gravitational wave passes, it distorts space-time, causing the mirrors to move slightly in response. This tiny change is detected by LIGO's instruments, allowing scientists to observe the most cataclysmic events in the universe, such as black hole mergers and supernovae. The birth of gravitational wave astronomy. LIGO's success has paved the way for a whole new field of gravitational wave astronomy. This allows astronomers to observe events that would otherwise be hidden from traditional telescopes, like black hole mergers. In 2017, LIGO made another key discovery: the merger of two neutron stars, GW 170817, which emitted both gravitational waves and electromagnetic radiation, light, providing a full spectrum of data. This multi-messenger astronomy is helping scientists understand the nature of neutron stars, nuclear processes, and even the origins of heavy elements like gold. Future detectors like LISA, Laser Interferometer Space Antenna, which will operate in space, will allow us to detect even more subtle gravitational waves, expanding our ability to probe the universe's most energetic events. When we observe distant stars or galaxies, we see them as they were in the past. The light reaching our eyes took billions of years to arrive, carrying with it an image of the universe long gone. Similarly, gravity behaves the same way. It carries information about the past, the echo of the past. The speed of gravity introduces a natural delay in how we perceive the effects of distant objects. For example, if the sun were to suddenly disappear, the Earth would continue orbiting its vacant position for another 8 minutes, the time it takes light and gravity to travel from the sun to Earth. This means that we don't feel the real-time effects of distant cosmic events. Instead, we experience echoes of the past. This is not just a curious quirk. It is a fundamental aspect of how the universe works. Every gravitational interaction is a snapshot of the past, and everything we observe in the universe, including ourselves, is influenced by the memory of gravity. Gravity as the universe's record keeper. This delay means that the universe has a built-in memory. Each gravitational wave, like a musical note, carries with it information from its origin, whether it be from the merger of black holes or the collapse of stars. These waves carry imprints of the objects that emitted them, revealing information that traditional telescopes can never capture. Einstein's theories of relativity helped us understand that space-time is not a passive backdrop, but a dynamic entity that responds to the presence of mass. Gravity moves through this fabric, carrying information about mass and energy. The speed of gravity ensures that causality, the relationship between cause and effect, holds true. Without this speed limit, the integrity of time would collapse. Imagine a scenario where information about the sun's collapse could reach the Earth instantaneously. In this case, the Earth might experience an immediate loss of gravitational pull, but continue to orbit in empty space until the last wave of light arrives. This delayed, finite propagation is the only thing that guarantees that the flow of time remains unbroken, protecting the laws of physics from chaos and paradox. The universe in motion. The speed of gravity serves as a cosmic metaphor for many fundamental principles of reality. At its core, gravity reflects the movement of time, from the past to the present, from cause to effect. Our observation of gravity is like hearing a story told by the universe itself, not in real time, but after it has traveled across the vast distances of space. The speed of gravity also serves as a reminder of our smallness within the vast cosmos. We are surrounded by forces that transcend our daily lives. Gravity, moving at the speed of light, is one of the most fundamental ways that the universe communicates with us. The limits of knowledge and understanding. As humans, we are constantly striving to bridge the gap between observation and understanding. Our measurement of gravity's speed has not only answered a scientific question, it has illuminated the very nature of reality. But this is only the beginning. What we know about gravity today may only be a fraction of what we will know in the future. Quantum gravity, which seeks to reconcile general relativity with quantum mechanics, may reveal deeper, more profound aspects of gravity's nature. As technology improves and our understanding deepens, we may find that gravity's behavior shifts in new and unexpected ways. Gravitational wave astronomy, a new era. The future of gravity lies in the continued exploration of gravitational waves. Instruments like LISA, Einstein Telescope, and Cosmic Explorer promise to push the boundaries of what we can observe. These instruments will allow us to study the dark ages of the universe, the formation of black holes, and even the potential discovery of dark matter. As we continue to push the limits of gravitational wave astronomy, we may discover that gravity is more complex than we ever imagined, perhaps revealing connections between gravity, dark matter, and the fundamental forces of the universe. Theoretical physicists are also exploring what happens when gravity interacts with quantum mechanics. Could there be tiny deviations in the speed of gravity under extreme conditions, such as near black holes or the earliest moments of the universe? Could gravitons, the hypothetical particles that mediate gravity, behave differently from our current understanding? As we venture into these new frontiers, we are bound to uncover more mysteries, adding new chapters to the story of gravity's speed. The speed of gravity is a fundamental aspect of the universe that links space, time, and the cosmos itself. It shapes how we experience reality, how we understand the fabric of space-time, and how we probe the deepest mysteries of the universe.